Hello, a great welcome to this tutorial on PLAXIS. Myself Jarajan P. This is tutorial 3 and demonstrates the verification of the Raft foundation for a given set of loads. This tutorial will be presented in two parts. This is part 1 of this presentation. So let me first take you to the problem statement. So the Raft foundation provided for a 5-story structure with a basement floor is shown here. The raft is of size 28 meters by 10 meters. So as you can see that it is essentially an 8-column structure, and the center to center of columns in the longitudinal direction is 8 meters and in the transverse direction it is 6 meters. So the raft is supported at a level 4 meters below the ground level. So the supporting layer essentially consists of a clay with the bedrock at 25 meters. The water table is at a depth of 8 meters below the ground level. So to provide the PLAXIS analysis, we consider a soil domain of size 80 meters by 4 meters, and the soil parameters used for the PLAXIS analysis will be the material constitutive model will be the Moore-Coulomb law, and the drainage type considered will be a drained type. The unit weight of the soil in the saturated and unsaturated condition will be taken as 18 and 16 kg per meter cube. Coming to the stiffness parameters, the Young's modulus will be taken as 6 into 10⁻³ kg per meter square with a Poisson ratio of 0.30, and the strength parameters will be coefficient C is equal to 10 kg per meter square, friction angle phi is equal to 24 degrees, and a divergency angle of 0 degrees. And the basement essentially consists of the basement walls and the basement floor. The basement wall will be having a thickness of 0.3 meters, whereas the floor will have a larger thickness of 0.3 meters. And for all, the material will be concrete that can be represented through a linear isotopic model. And the E value is assumed as 2.5 into 10⁻⁷ kg per meter square with a Poisson's ratio of 0.15. So let us start the PLAXIS modeling. Okay, fine. So we will start with the project title. So we'll just write down verification of Raft foundation. Again, so next, let us define the limits of the model. So as already discussed, the soil domain will be of dimension 80 meters by 40 meters. So this means that my x minimum I will choose it as minus 40, and my x max it will be plus 40, and my y minimum it will be minus 20, and my y max it will be plus 20. So this means that we define a soil domain of dimension 80 meters by 40 meters. So that's okay for us. So as you can see that yes, the model is domain is already defined over here. So let us proceed now to define the soil stratigraphy. So this will be defined through the borehole. So let us place the borehole at the right of the origin. So as you can see that yes, this is we have to place it at 0, 0. So that means just zoom it. So we can place it anywhere. So but okay, fine. So this is at the origin. Okay. So now let us start defining the layers. So as we know, it consists of a single clay layer. So let us add that clay layer. So here the depth of the clay layer will be of 25 meters. So let us define the bottom as minus 25. Okay. So this means that as you can see that yes, it is defined from 25 meters, and the water table will be considered at a depth of 5 meters. So we can have it as a minus 5 meters. So let me just cross check it once again. Okay, it is 8 meters. So this should be not 5, it should be minus 8, minus 8.0. Okay, so you can see that yes, the water table is now at a minus 8.0 below the ground level. So now let us proceed for defining the material. So this can be done straight away from this mod. So let us suppose the materials. Define the set type as the solvent interfaces, because we are going to define the material as the soil. So new. So let us provide the identification as a clay, and it will be the Moore-Coulomb drain type analysis, and the unsaturated and the saturated, let us take it as for example 16 and 18. That's good enough for us. So we don't want to see any advanced parameters right for the time being. So let us proceed for the parameters. Here E we will define it as a 6E3. So it will be 6E3, that means 6000 kilometer per meter square with a Poisson's ratio of 0.30, and then we have the automatically calculate the G and the odometer modulus that is presented over here. Let us straight away jump to the strength parameters, wherein the quotient will be defined as say 10 kilometer per meter square. So we can just type it as a 10, and the phi value it will be taken as 24 degrees, and the corresponding dilatancy angle will be 0 degrees. So that's all regarding the definition of the soil. We have defined the E value, we have defined the C and the phi values. Okay, and the PLAXIS has automatically calculated other important parameters like G, odometer modulus, and the other, for example, the shear wave velocities, etc. Here we assume that the stiffness and the strength do not vary with respect to the depth. Accordingly, we'll keep the advanced parameters at default. So that's okay for us. Okay, so now let us assign this clay material to this borehole. Simply drag and drop over here as usual. Okay, so this is okay for us. So this means that we have defined the soil stratigraphy, the soil material, we have defined the water table. So this means that as far as the soil is concerned, the definition is complete for us. So let us erase it. So you can see that yes, this is the soil model, and we have a borehole that is placed at the center. So having completed the soil mode, let us proceed to the structures mode. Obviously, the purpose of the structures mode will be to generate the basement floor, which consists of the walls as well as the floor. So go to the structures. So here, when you go to the structures, you can see that automatically this soil color, everything is made transparent for easy navigation. So here, as we did in the earlier tutorials, what we do is that first we create a surface, we extrude it, and then we will decompose this volume into surfaces, and then delete the unwanted volumes as well as the surfaces in order to obtain or in order to model the required surfaces. And after modeling the surfaces, we'll convert these surfaces into the plates and then assign the required properties to the plates. Okay, so let us proceed. So as already discussed, we know that the raft is of dimension 28 meters by 10 meters. So we can straight away go for the create a surface. Okay. So what I will do is that I can just generate a surface, something like this. Okay. Okay, fine. So let us just start defining it. So first, obviously, we'll have it is a 28 meters by 14 meters, 10 meters. So the first, I will go to start with the third quadrant. So it's a minus 14, and y will be my minus 5. And then I will go to the second one, that is a plus 14 with a minus 5, And then I will go to plus 14 and with a plus 5, and then we'll go to minus 14 with a minus 14 with a plus 5 and remember that this surface is generated at set equal to 0, that is at the ground surface. So this is okay for us, fine. So you can just zoom and view whether this surface is properly created. Yes, it is properly created. Now let us extrude this surface in order to create a rectangular volume. Okay, so what we can do is we can straight go to this menu which shows the extrude object. Okay, so we will select. Obviously, we know that the extrusion depth we want this to be taken to minus 4 meters, right? We know that the supporting level of the raft is 34, so we'll keep it as minus 4. Okay, so you can see that yes, it is extruded downward direction by 4 meters. So we can say that apply. Okay, so fantastic. So we have created now a volume over here, and as you can see that the selection explorer obviously shows you the new volume that is created. Now our purpose is now here right now we have got a volume and also we have a surface. Now let us say extrude the volume. Okay, right before extruding the volume, for simplicity, Let me just delete this surface. You can see that we have got a polygon one here. So let me just delete it. So you can just right click on the surface and then just press the delete. Okay, so that is already deleted. Now let us explode this surface into this volume into surfaces. Right click, and we can say that here it is a decompose into surfaces. Just a decompose into surfaces. Okay. So here you will find that yes, many surfaces have been created. Okay, for example, if you go to the geometry and the surfaces, you'll find that yes, many surfaces means that we have got obviously 1, 2, 3, 4, 5, 6 surfaces are created. Okay, of which we require 5 surfaces. So let us delete the unwanted ones. So here we have got a top surface that is again created. Just delete it, and then as you can see that on the top we have got a volume. Just delete it. So now you will find that we got the required basement floor that consists of essentially of 4 walls as well as a basement floor. So this is good enough for us. Now remember all this is right now the 5 surfaces are the surface entities. So now let us first create all of them into convert all of them into the plates. So select the multiple surfaces. You can press the control key out of the multiple selections. So you can convert this into, so here we can say that we create a plate. So you can say that yes, the normal and the tangential direction are shown here. And you can also select the bottom one. So right click over here, create a plate. Okay. So you can just use the camera option over here. And you can see that yes, this is the bottom of the raft and these are the side walls. Okay, fine. So now we need to define basically the plate properties before assigning these materials to the surfaces. Okay, fine. So let us proceed for defining the properties of the basement wall as well as the basement floor. So we'll straight away go to that the material. So here select the set type as a plates. So create a new one. So first we shall select the basement wall. Okay, fine. So that's identification, and then we shall use the thickness for the wall. We will be using a thickness of the plate as a 0.3 meters, and the unit weight will be a 15 kilometer per meter cube. See, we are setting a lower value because there is always a interference between the soil elements as well as the concrete elements. So we are using, to take care of that, we are using a lesser unit weight, 15 kilometer per meter cube, and we are using a linear isotope material with an E value of so we can use it as 2.5 into E7. So 2.5 E7 kilometer per meter square, and this isotopic, so it will be set same as the E1, and the mu value less than 0.15. So that clearly defines the properties of the basement wall. So this is okay. So now the basement, let me select the color, the proper color for the identification. I choose just my color. Okay. Now my basement raft or the basement floor, the material property will be the same as that of the wall, except that the thickness will be slightly larger, that's 0.6 meters. So what we can do is that we can just select this and we can just copy this. So we'll have it as this as a basement floor, and let me select the color a slightly different one so that is easy for so let me just edit this. So this is a basement floor. So for the basement floor, we know that all the parameters remain the same. Except only thing is that we have to change the thickness from 0.3 to 0.6 meters. So that's okay for us. Now we have defined 2 basement materials. So this is okay. Now let us start assigning this. So it's a simple task. Let us just select, for example, the side walls first. So set material. This is my wall. So I will select my wall, and again go over here, select my property as the wall. Okay, and again go over here, select the property as my wall. And again go over here, select here my property as the basement wall. Okay, so you can say that yes, for easy identification, we have seen that all the properties are being created for the side walls. Now let us straight away go to the basement floor. Here we'll be choosing the material as the basement floor. Okay, so that's okay for us. So this means that we have completed the assigning the various properties for the walls and the floors. So you can just see the rotate camera, and you can see that all the walls and the floors are assigned different colors based on what we call as the material properties. So this means we have completed the definition of the structural elements, that's the basement walls and the floor. Now obviously we are not going to define any columns of the structure for this case. Instead what we will do is that we will straight away proceed for a definition of the points, and these points will be straight away representing the columns, and we know that we have six columns that is spaced it is in the longitudinal direction. So let us proceed for defining the point. Now here the problem is we need not to define the points and the point loads separately. Rather we can straight away start defining the point loads here. Okay. So let me, before going to that, what I want to do is that I want to as you can see that this is a 3D view, right? I want to select only a level, okay, that corresponds to my basement floor, that is at set equal to -4. So what you can do is that you can straight away go to the top view, and the top view available we have anything, nothing. Okay, so we can say that here I will choose it as -4 so that my cursor will be restricted to this level. Okay, so you can say that set this. Okay, so as you can see that once you move over different dimensions, set remains as -4 only. We are at the basement floor level only. Now let us start defining the various point loads. So what we can do is that we can straight away zoom this particular portion, okay, and take this, and let us start defining the point loads now. So here as you can see that we have the point create point option, right? So if you press it, there's an option also to create a point load, because we want to generate the point loads only. So just press it. Okay, now what we can do is that so as you move, you can see that the different coordinates. The first one will be obviously is a 4 plus 8, that's a -12, -12 and -3, right? So that will be the first point load is defined. And the second one will be obviously that's the -4. So we have got -4, -3, and then we have got a +4, -3, and then we have one more, that's a 12. Okay, 12. So this means that the bottom four point loads have been defined. Now let us go straight to the top. You can see that's 12. We have got a +3. Okay, define that. And then we have obviously will be another 4, 4 with a +3. Okay, and then we need to define here it is a -4 at a +3, and then final point that is a -12 with a +3. Okay, so this means that we have defined the point loads properly. Now as you can see, for example, if you select any point, so you can see that for example here the point 1, and you can see that by default it has generated a unit load -1 kilonewton applied at it. So at all these 8 points we have applied the so-called unit load in the downward direction, and we'll modify this unit load when we proceed to the staged construction later. So for example here you can see that if you go to the loads, so this is for example the point loads. Here you will find that we have defined 1 2 3 to 8 point loads that corresponds to the 8 columns, and you can see that they are being appropriately modeled at the right locations, that is at set equal to -4. Okay, fine. So having done that, now I think we are ready to move to the mesh mode. Okay, so proceed to the mesh, and in this mesh mode, first of all what we need to do is that let me just zoom, raise the zoom level. Okay, so means that let me just go to my perspective view. So here obviously we know that the raft will be loaded. Okay, it means that we need to refine the basement floor to a very small scale compared to the soil model. So first of all, what we can do is that let us first remove the soil portion that is occupying the raft volume. So we can go straight to, for example, here geometry, go to the soil volumes, generator volumes, just remove this. So you can see that yes, so we can just zoom this a little bit over here, right? And we can also slightly rotate it so that we see the surface properly. Okay. Now let us proceed for defining the local coarseness. For example, if I select that bottom floor as a basement floor, you can see that right now we have got a fineness factor of 0.5. I want to change it to, for example, 0.25. That means a little bit more fineness. So what we can do is that press this refine mesh option, select this object, you will find that it is again reduced to 0.35. Again, select it, it is 0.25. This means that we have meshed the bottom basement floor to a very small scale compared to the soil. So now we can go for the global meshing. So let me just reserve the zoom button over here. Now I can straight away go for the generate element distribution as the medium. And so this is okay for me. You can see that the meshing is in progress. We'll be able to visualize the meshes generated after this meshing operation. So let us wait for that may take say 5 to 10 seconds, not more than that. So what is very important is that it is up to the designer to see the meshing, selecting the mesh sizes. In some complicated cases, we may have to perform some preliminary analysis to see that the mesh size selected are proper. So let us visualize now, view the mesh that is generated. Okay, so yes, okay, fine. So okay, we find that now it is occupied by the soil. So as usual, we can go to the geometry, we can go to that soil volume, and we can just make it off. Okay, so yes, so this is the soil mesh that is generated. So you can see that the basement floor that is provided with a finer mesh compared to your basement walls. You can see that basement walls are having a little bit larger meshes, okay, and the soil is also having a larger mesh. So this means that having generated the mesh for the model, we are now ready to proceed to the so-called stage reconstruction module, and we'll discuss the stage reconstruction module in part 2 of this tutorial. Till then, bye.